And again, we can generalize this to higher dimensions. For instance, you have a joint random vector of size n, of dimension n, and you would like to obtain the marginal PDF of the kth component, x sub k. So in order to obtain that, you will integrate the joint PDF with respect to all the remaining components, x1, x2 through xk minus 1, xk plus 1 through x7. If you integrate the joint PDF with respect to all of these, you get the marginal PDF of xk. Okay, for instance, well, here you have a joint PDF of x2, x4. Let's assume we have a joint PDF of dimension 5. Okay, so if I integrate this with respect to x1, x3, and x5, all of them ranging from minus infinity to infinity, what I get is, well, what is remaining here is x2 and x4. So the joint PDF of x2 and x4. Okay, and then, for instance, if you integrate this with respect to x4 from minus infinity to infinity, you get the you get the marginal PDF of x2. Simple as that. Okay, next we will talk about conditional distributions. Again, the definitions are the same with respect to single random variables, so I will just generalize them here. The conditional PMF, in case we have a discrete distribution of x1 given the value of x2. So this is the probability of x1 being equal to parameter x1 given the value of x2, which is given here. Okay, sometimes you may not see this here. Sometimes here you can see, instead of the value parameter x2, you might see the random variable here. So that means you have the value of x2, but it is represented by a generic placeholder, let's say, instead of a specific value. So here, well, this is just a conditional probability. Okay, we have dealt with this since week number 2. So this is this event intersection with this event. Okay, probability of that intersection divided by probability of the condition by definition. So that is probability of x1 equals parameter x1 and x2 equals x2 over probability of the condition, random variable x2 equals parameter x2. But this one here, you see, by definition, it's a joint PMF. Joint PMF for x1 and x2, evaluated parameters x1 and x2, divided by, you see, this one is the marginal PMF of x2. So the conditional PMF of x1 given x2 in general is equal to the joint PMF of x1 and x2 divided by the marginal PMF of x2. So this is quite similar to the definition of conditional probability. So here we have a conditional PMF, and its definition very much looks like the definition of conditional probability. And we can also generalize this. The conditional PMF of x1 given the values of x2 and x3 is, well, this conditional probability. If you just apply the definition of conditional probability, this is what you are going to get. The joint PMF of x1, x2, x3 divided by the joint PMF of x2 and x3, because in the condition we have 2. Or for instance, the joint PMF of x1 and x2 given the values of x3 and x4 is equal to the joint PMF of x1, x2, x3, x4 divided by joint PMF of x3 and x4, which are the given values. Okay, you can deduce other forms you can yourselves. And these are conditional PMFs, and conditional CDFs, quite similar. If we have discrete distributions, you can just write this as, well, by definition, instead of the equality here in the PMF, we have any inequality here, less than or equal to relationship. So the conditional CDF of x1 given the value of x2 is equal to, by definition, the probability of the event x1 less than or equal to parameter x1 given the value of x2. Okay, so this here is a known quantity. This is not an event here in terms of inequalities, it's an equality. Okay, be careful with that. And this, by definition, can be written as the sum of conditional PMFs evaluated at values for the first one, first component, where they do not exceed x1. Or in general, for instance, you can write the joint conditional CDF of x1 and x2 given the values of x3 and x4. This is equal to this double sum where you have the conditional joint PMF of x1 and x2 given the values of x3 and x4, while the first component does not exceed x1 and the second component does not exceed x2. Okay, these are just based on definitions. If you learn the definitions well enough, you can derive these by yourself.